Hello, greetings everyone. My name is Derek. I'm an LD full stack engineer, and today we are going to solve a small problem right here on Hacker App. Basically, it's all about articulation points and bridges. We are talking about algorithms and graphs here. So let's jump straight to it. First of all, here's the problem. We're going to use Python. So before we start, even let me just inform you that you need a prerequisite of understanding a bit of graphs, bit of algorithms, and also Python at least to the intermediate level. That being said, let's jump straight into it. Here's the problem. Given a connected graph with n nodes and m edges, where m is less than or equal to n, you're also given two nodes a and b of the graph. You need to find the number of edges which are present in all paths between a and b. So here are the constraints. As you can see, they are on the screen. I've highlighted them. Now, the input format is the first line contains two space separated integers n and m, the number of nodes and edges respectively. The second line contains two space separated integers a and b. Then m lines follow. The ith line contains two integers xi and yi, and these are the end points of the ith edge. So here's the output format, which should contain a single number, which is the number of edges present in all paths between a and b. So that being said, let's just try and think, what does this question really mean? Okay, what is this question trying to get us to do? So this problem requires us to find the number of edges that are present in all paths between two given nodes a and b in a connected graph. The graph has n nodes and m edges, okay, where m is less than or equal to n, and the constraints are as I had explained right here. So now the input here will consist of the number of nodes n and edges m, the two nodes a and b, and a list of m edges represented by two nodes. Now, this output should be a single integer representing the number of edges that are present in all the paths between a and b. So let's think of how are we going to solve this. So our solution will have 4 steps. I'll just write them here and then we'll erase them once we start coding. So we'll have to find the bridges. Okay, another thing we'll have to do is to build a bridge tree. Another thing we'll have to do is to do some pre-processing of the LCA, that's the lowest common ancestor, and then we are going to finish by querying the result. Alright, so that being said, let's see how these things will work. So when finding the bridges, finding bridges helps to identify the bridges in the graph using Tarjan's algorithm. A bridge is an edge whose removal increases the number of connected components in the graph. Okay, when you go to building the bridge tree, now we'll construct a tree where each node represents a biconnected component, that is a component without bridges of the original graph. Then pre-processing for LCA. Now here we shall prepare the bridge tree for lowest common ancestor queries using binary lifting, and then querying the result, we shall determine the number of edges that are present in all the paths between a and b by finding the lowest common ancestor of the components containing a and b. Now again, let me just speak a little bit on the prerequisites of going through this. You need to have some graph theory basics, that is understanding of graphs, nodes, edges, and connected components. You need to also understand Tarjan's algorithm, which is the knowledge of how the bridges are found in a graph. We also need to know a little bit about biconnected components, which is actually understanding how they relate to the bridges, and the LCA, or the least common ancestor, which is familiarity with LCA in trees and binary lifting for efficient LCA queries. So now let's see, what shall we use here in our solution. In our solution we shall use Tarjan's algorithm. Tarjan's, let me just write it well. Tarjan's algorithm. We will also talk about, or rather use, the depth first search. We will also talk about the binary lifting. Yeah, and the Tarjan's algorithm shall be used to find bridges in the graph. The depth first search will be used to build the bridge tree, and the binary lifting to pre-process the bridge tree for efficient LCA queries. So how does this our solution seek to answer this question? Now, this solution identifies the bridges in the graph, which are edges that are critical for connectivity. By building a bridge tree, it groups nodes into bi-connected components. The LCA of the components containing A and B in the bridge tree gives the number of bridges, that is the edges that must be traversed in all paths between A and B. So now, before we start, we need to do some importation here, and I'll explain it in a bit. So let's just so the language I'm using here is Python 3.8.10, Python 3.8.10, and so here is how we shall be doing this. So import sys, sys is actually used to handle large input efficiently, and then from collections import default dict and dequeue. Okay, default dict helps us to construct adjacency lists dynamically. Dequeue is used for the traversal of the depth first search here. Then we shall set recursion. So that's this, yeah, sys dot set recursion limit to 200,000. Okay, all right. So now the next thing here shall be finding bridges. So this is the first step, as we had said. So let me just comment it here. Just comment it. Finding bridges. So here we shall declare a function. So we call it def find bridges. So we have the parameters u, parent, timer, disk. I'll tell you what these are in a bit. Log, graph, bridges. Yeah. So now when you get here, we know that we are about to use Tarjan's algorithm. To find the bridges in O, V plus E. This is the time complexity here. So now, as I had said a bit earlier, I'll tell you what these are. Now, disk U will be the discovery time of node U. Okay, so let me just code it as we explain it. So disk should be in lowercase. Disk U so disk U is the discovery time of node U. Now this keeps track of when the node U was first discovered. Note this, first discovered, using the depth first search. Then low U is the lowest discovery time reachable from U. Now this one keeps track of the earliest discovered node that can be reached from U. Okay, then timer 0, this is now a counter. See, this timer 0 is a counter to keep track of the discovery time. Now this is a list with a single element to allow modification within the recursive function. The bridges, this is now a set to store the bridges that are found. Okay, these will store the edges that are bridges in the graph. Okay, so let's get on with it and code it and see how it comes along. So we have timer increment by 1, and for v in graph if v is equal to parent continue if the disk of v with the discovery time of v is equivalent to -1, then basically, you see, you cannot measure time backwards, so if it's not visited. Alright, so let's try and find them bridges. The bridges, should I say find bridges? Yeah, so we have v u timer, we have the disk, we have the low, we have the graph. Yeah, basically it's this list, this set over here, or rather parameters, and then we have the bridges. So now let's add some logic to it. So low of u is equal to minimum value between the low u and low of v. Okay, so now if low v is greater than disk u, disk u, then we have bridges dot add we have u and then v, or and also you can do bridges dot add v and then u, else else we have low u is equal to the minimum value of low u and disk v. So this is actually the first step. You see that step for finding the bridges, this is it. So let's talk a little bit about this code before we proceed to the next part of it. Yeah, let's talk a little bit about this code before we talk about the next part of it. So as I said earlier, disk u is the discovery time of node u. This one actually keeps track when that node u was first discovered during the depth first search. Now low u, you can see where it appears even here. Low u is the lowest discovery time reachable from u. This one keeps track of the earliest discovered node that can be reached from u. Timer 0. Now this is a counter that keeps track of the discovery time. This is a list with a single element to allow modification within the recursive function. Now the bridges, this is a set. Bridges here is a set. Okay, let me just show you where it is. The bridges is a set. Okay, this one here. Bridges is a set to store the bridges found. These will store the edges that are bridges in the graph. Sorry. Now this function uses Tarjan's algorithm to find bridges in the graph. It performs a depth first search and updates the low and the disk values for each node. If a back edge is found, note this, if a back edge is found, it updates the low value. If a bridge is detected, that is low v greater than disk u, then it adds the bridge to the set. I want to believe that up there we are very clear, so we can proceed. Now let's continue, and now we want to start building the bridge tree. So I'll just come here and comment building the bridge tree. Okay, so now we are now supposed to do the next step, which is actually to build this bridge tree. And what are we about to do right now? When I introduced this thing earlier, I said we had 4 steps. The first one is finding bridges. That one we have done. Building bridge tree. Here we are constructing a tree where each node represents a biconnected component. Okay, that is a component without bridges of the original graph. Okay, that being said, let's jump straight into it. So we have def, we have build bridge tree. So here we have n, we have graph, we have bridges, and so in this one we have builds a bridge tree using the DFS. This one builds bridge tree using the DFS, and it groups, so grouping nodes into components. Okay, so now let's jump straight into it. So we have visited is equal to false. False. Yeah. Component. So I'll explain to you what these are in a bit. Let's just code it right now. Then we have comp id is equal to 0. So basically, what are we talking about here before we go further, so that we are on the same page? So visited is a list that keeps track of the visited nodes. This one ensures that each node is processed only once. Component is a list to store the component ID of each node. Now this assigns a unique ID to each by connected component. Alright? Then we have comp ID. This is now a counter to assign unique IDs or identification to components. This is incremented each time a new component is found. Okay? This is incremented each time a new component is found. Alright, so we move on. And before I continue, let me just tell you that a tree is a dictionary. Actually, the tree we have been talking about all along. This is a dictionary to represent the bridge tree. This will store the connections between the connected components. Okay, so let's get in and do the actual coding here. So we declare a function, call it dfs, and here we call it node. Here we have a node here, and so we have stack is, so we have a node. So while stack so u is equal stack dot pop. If visited u, then we continue, then visited u is true. Component u is equal to comp id. So for v in graph u, if not visited v and uv, also not in bridges, then we append this to the stack. So stack dot append v has now been appended to the stack. Yeah, I believe we're following closely this logic. So now we come back here, so for I in range n, range, let me just put it nicely. Yeah, that's better. Range n, if it's not visited, then the DFS I. So we now call this function with I as the parameter, this function that you have declared up here, DFS with node parameter. Okay, so DFS I, then we have the comp ID, we increment it by 1. So now let's come to the tree we have been talking about. Yeah, so let me just move this up a little bit. Okay, so now the tree is equal to, or rather the tree is the default dict. Remember I said the tree is a dictionary. Yeah, so we shall convert this list into it, and so we have for u and v in bridges, so we have comp u and comp v is going to be component. We have u here and component v. So now if comp u is not equivalent to the comp v, then tree, we have comp u dot append comp v, and we also have tree comp v dot append comp u. So now what do? We return tree, we return tree and the component, and then the comp ID. Let me explain this a bit so that I don't lose you here. When you talk of visited is actually a list that we use to keep track of those nodes that have been visited already. And this one will ensure that each node will be processed only once, not twice, thrice, no, only once. The component that we have been talking about here, the component is also a list. That's why you can see we are appending things onto it. The component here is a list. Let me just remove that space. Component is a list that stores the ID of each node. This assigns a unique ID to each biconnected component. The comp ID is a counter to assign unique IDs to components. This is incremented each time a new component is found. The tree is a dictionary to represent the bridge tree. These will store the connections between the biconnected components. Now this function that we have just talked about here, this function, the build bridge tree function, it actually builds the bridge tree by grouping the nodes into biconnected components using depth first search. It then connects these components using the bridges that were found earlier. Remember the step 1 that we had, finding the bridges? Yes, those ones are the bridges we're talking about here. So we are now entering the next step, and this one is basically the pre-processing of the lowest common ancestor. So that being said, let's see, what are we going to be talking about here? We need a function here that will pre-process that bridge tree that we have just created for LCA queries using the binary lifting. Now this one performs breadth first search, or rather BFS, to fill the depth and parent arrays, which are then used to find the LCA efficiently. Okay, that being said, let's code a little and then we'll explain as we continue. So def pre-process LCA, and here we have tree, we have root, we have a number of nodes. So now, what are you going to be doing here? Here we're going to prepare. So this one actually prepares the bridge tree for LCA queries using binary lifting. So now we have parent is equal to multiplied by the number of nodes for in a range 2 0. Then we'll have depth is so we again have another function within this function, and we call it BFS. We shall use lowercase letters here. It doesn't change the performance anyway. Get the Q is equals to DQ, and here we shall have root. So the depth of this root will be 0, and then while Q will have U is equal to dot pop left so for V in tree if depth V if always you find that you're putting depth of something to be -1, just know that that thing is unvisited. Okay, yeah, that's a very important point for you to note, so that we are reading from the same page. And so here we have depth V depth u plus 1. Then we have a parent 0, and we have v here equal to u. Then you have q dot append v. So now we call this function the BFS function. Now we know that for I in the range of maybe 1 to 20, then inside this for loop we have another one for u in the range of the number of nodes if the parent I minus 1 then we have u here is not equal to negative 1. So we want to make sure that something is not unvisited. So the parent I, of course u is equal to parent I minus 1 with the parent I minus 1 u. No, actually not I minus 1 u. Yeah, this looks better. So we continue, and so as we continue with this, we can now return the depth. Okay, yeah, we can now return the depth parent. So what is parent here? Parent is actually a two-dimension list. Parent is a two-dimension list that we use to store the ancestors of each node for binary lifting. This one allows us to jump up the tree in powers of 2. Okay? Yes, and the depth here basically is a list to store the depth of each node in the tree. This one now keeps track of how far each node is from the root. The BFS, this BFS here, this one, the BFS is a function to perform breadth first search and fill the depth and the parent arrays. This one initializes the depth and parent arrays for the root and its children. Now this function pre-processes the bridge tree for lowest common ancestor queries using what we call binary lifting. It performs a BFS to fill the depth and the parent arrays, which are then used to find the LCA efficiently. Okay, that being said, I think it's time to go to the final step, which, let me just comment it here. Please don't forget the steps you have taken. First of all, we are finding the bridges. Secondly, we were, first step, we're finding bridges. The second step, we were building the bridge tree. The third step, we have just pre-processed the LCA. The fourth one, we are now querying the result. Querying the result. We need to know whether we are right or wrong. That being said, I think this is going to be our last step, and it's going to be very, very important here. And so a lot of things here will be recurring, so I will not explain them in that much of detail, but then I will be explaining as we code along. So yeah, so let's get on with it. Okay. So here we will talk about find LCA. This will be a function that will find the LCA of two nodes using binary lifting. This function will first ensure that U is the deeper node, and then uses binary lifting to find the LCA. Okay? Yeah, and then we're going to define the main function also, which will read input, it will build the graph, it will find bridges, and it will build the bridge tree, pre-process it, and it will also pre-process the LCA and query the result. That one will orchestrate this entire process that we have been designing for the past 40 minutes or so. Alright, so let's continue. So we have U, V, depth, parent. So here we are going to be finding the LCA of two nodes using binary lifting. So now if depth of U is less than the depth of V, then we have U, we have V equals to V, and then U. So here we have diff, or rather the difference, but then let's just call it diff. We have depth of U minus the depth of V. And so for I, in the range, which range do we take? Maybe take, for example, 20. If the diff and here we have 1, so we have U is equal to the parent of I and U. So if U is equal to V, return U. For I in range 19, -1, -1. If the parent, if I is not equal to the parent of I and V. So we have U is equal to parent I U. V is equal to parent I and then V. So here we return the parent 0 U. Okay, now this is just the else here. Now we are about to get to the main function. Remember, the main function executes everything here. It's the one responsible for calling all this and putting it together to solve the problem. So let's see how we do it. So we call it def main. So the input, standard input, then we have data, input, dot split, so here we have n, we have m, so what will be the int, and the int. So here we're going to have the data, the 0, then we have the int data 1. Yeah, this was to close this one. I just have it. And then we're going to be having A and B. Sorry, A and B, int data dot 2 minus 1, int data 3 minus 1, edges data 4. So now let's see building the graph. Build graph. So here we're going to be having graph is equal to default dict list, yeah, for I in range 0 to by m, then to u v u v int edges I minus 1. Then you're going to be having int edges I plus 1 minus 1. Graph U dot append V graph V dot append U. So here's the first step that we're going to be having here, and let me just highlight it or put it here. Call it step 1, finding bridges. So how do we find them? We have to find the bridges, we have to discover them. Okay, to find the bridges we have to discover them. So we have disk is equal to phi n. Then the low, remember what low is, remember what disk is, we discussed it a few moments ago, times n. We have timer, also remember its role, set it to 0. We have bridges, set, we have for I in range n, for I in range n, we have if disk I negative 1 find bridges I negative 1 timer disk low graph bridges. So let's proceed to step 2. Step 2 is building bridge tree. Basically what I'm doing here, I'm just trying to get what you have been doing all along together to see how it comes to work, so that you can see the sense out of it. So you have tree component, we have a number of components, then we have build bridge tree. Now that takes n, that takes graph, it takes bridges, okay, to build this tree. Then now we go to step 3 now. Step 3 is pre-process for LCA, and here we're going to have the depth and the parent. The pre-process LCA, we have the tree, we have 0, we have a number of components, So let's go to the final step and see if this works at all or if it doesn't. Step 4, we're going to query result. Okay, so how do we do that? We're going to have comp, so we comp A, comp B, it's going to be component A and component B. If comp A is equal to comp B, then we can print 0. Remember the 0 that needed to be printed at the end of the question if everything is correct. Else, alright, if that's not happening, then the LCA is going to be find LCA. We have comp A, comp B, we have depth, and we have the parent. Alright, so the result is going to be the depth of comp A plus depth comp A plus depth comp B minus 2 times depth of the LCA, and print the result. Now let's call this main function. Alright, let's just call the main function. If name is main then run this function main. So basically this is the solution that we have developed, and so we need to see if it runs or if there is a problem somewhere that we can fix. Alright, so this being said, let's see how it runs. Let's see how this thing runs. So we go ahead and test it to see if our solution indeed is working. I'll just come to here and then compile and test code, then sample test cases passed. Okay, in this case HackerEarth tests with the sample input of theirs, and so let's submit the code. As you can see, all our input has been accepted, and now this means that our solution indeed solves this problem. And so let me just talk a little bit about what our solution did and why it is and what we just did. So this solution is efficient, and it leverages several advanced graph algorithms to solve this problem within the given constraints by identifying the bridges and constructing a bridge tree. It also reduces the problem to finding the LCA in a tree, which is well known and effectively solvable problem. The use of binary lifting ensures that the LCA, or the lowest common ancestor queries are answered in logarithmic time, making the solution scalable for large inputs. Now, why would we say that our solution is the correct? Because when you look at Tajan's algorithm, it correctly identifies all the bridges in this graph. I can assure you that the correctness of bridge tree construction is also there, because the bridge tree correctly represents the biconnected components and their connections via bridges. Also, we can talk about the efficiency of the LCA queries. The binary lifting ensures that the LCA queries are answered efficiently. Alright, this makes the solution suitable for large inputs. Also, in handling edge cases, the solution correctly handles edge cases such as when A and B are the same node, or when there are no bridges between them. This solution now is both correct and is efficient, making it the most appropriate approach for the given problem. Okay, now that is what we have done. Thank you very much for your patience. Just for a short review, let me just say that we did only 4 things here. We found bridges, we built a bridge tree, and we pre-processed for LCA, which is the lowest common ancestor, and we queried the result. Thank you very much for your patience, and I'm hoping to see you again in another video. For now, bye bye.